With that, let's look at some applications of the suffix tree. Now that it's fresh in everyone's memory what suffix trees are, let's motivate why they are so useful and popular before we spend more time on thinking about how to construct them. Just to reiterate, we're storing suffix trees like this if we represent them in a computer. So that's if you want to analyze space and time, you should think of this. But for designing algorithms, we'll think of the representation on the right, just because that's the same information, just stored differently and much more human-friendly. A little nitpick or extra little thing that sometimes is important and is not a problem. We assume that every internal node has a quick way to jump to one of the leaves. And just as a tiebreaker, we assume that every internal node in here has a pointer to its leftmost leaf, which could be silly here if it's just the child, but you know, it could be in all of these examples, it's just one edge. Oh, come on. In principle, the tree could be fairly big, the subtree of a certain internal node, and it's not guaranteed that you can jump in one step to a child, to a leaf in all cases. But in our example, it actually is. I guess it also depends on how you order the children. We'll just make this assumption to analyze algorithms to make the analysis a bit easier. So when you have an internal node, you can quickly find one of the leaves in its subtree. I don't think I'm using this a lot, but sometimes just as an abbreviation, ti is the ith suffix, starting at position I. Okay. Now, before I present you the solution, maybe you can figure this out. If we have a suffix tree like this one, that's the same as on the previous slide. What does that tell us about occurrences of this pattern A and A? I teased the whole unit as saying we'll do text indexing, we'll find patterns in the text quickly. Now I've spent a lot of time talking about tries and suffix trees without making the connection. So it's time for that. I'll show the big tree instead. The pattern is A and A. Well, this one I don't really expect you to see it yet, but I thought it's useful to first trigger you thinking about it before I give the solution away. Okay, more votes come in, 27. We do again the 35. One more, 34. Okay, awesome. So many votes for many answers. There's also many correct ones. Okay, as always, you resist the urge to change your answer much. Let's switch back. Hopefully it doesn't tell us nothing. It occurs, it tells us that P occurs in T, and I'll show you in more detail why. And it also tells us something about where, what indices. And we can deduce from that how often. Let me just have that on the next slide, I think. But at least we want to draw this picture. So what's the connection between a collection of all suffixes and pattern matching or string matching? The reason is just if a pattern P occurs in the text T, then it is a prefix of a suffix in T. That's just throwing some fancy words around. So if that's our text T and we have our pattern occurring somewhere, then there's a suffix of the text starting here. That's some TI, where P is a prefix, occurs at the beginning. All right, great. What does that help? One thing I haven't emphasized about tries, but you could have maybe figured that out yourself. You can actually search for things in the dictionary that have a certain search as the prefix. Let me do that here first. So what happens if we just traverse with A and A in our suffix tree? Start at the root, A, N, A. We end up here. That's what happens. What does that tell us? It tells us that, first of all, we didn't fall out of the tree. So we didn't get stuck in some way. And following this green pointer, or just looking at the subtree here, we see there's two leaves. So there's some way to continue from A and A to a longer string that's stored as one of the leaves. In our case, the leaves are not arbitrary strings, but they are the suffixes of our text. So there are two suffixes in the text that I can find by reading A and something else after that. So both of these suffixes have A and A as a prefix, which says at positions 1 and 3, there's an occurrence of A, and that's all the occurrences that there are. So in a way, the suffix tree encapsulates, or the subtree we reach by finding the pattern encapsulates everything we need to know about the matches in the text. That's why suffix trees are so cool. They have all that information tidily collected in one node, and then we just have to walk around this subtree. In a little more structured way, that's what I have on this slide. So we try to traverse with our pattern in the tree, following the next edge when we can, like in our example, A and A went nicely through. And then there's different cases what can happen. So we had example A and A, where colloquial I would say we traversed in the suffix tree and we ran out of pattern. We reached the end of the pattern. A and A brought us here. And so if that's the case, we find all the leaves in that subtree. That's all the occurrences of that pattern. Now, there are also slightly different options. If you have the, say, the pattern BA, you would start traversing this edge, and then you're stuck. You run out of pattern in the middle of an edge. I mean, figuratively speaking, it's remember it's actually a compact trie, so you wouldn't really get stuck in the middle of an edge, but you could match a prefix of the edge label and then you run out of pattern. Turns out this is actually the same as if you were just going to the next node below. If you just complete reading the edge and ignore that, you also get all the occurrences are in the subtree. A different case occurs if we fall out of the tree. Say the pattern NB. We start here, we go here, and then B is not in the tree. There's no child edge to follow. That means NB doesn't occur anywhere. So we can get stuck in two ways. We can get stuck at an internal node, like in this case. Then there's just no child edge for this. There's a variant of this where we can traverse an edge, but then we fall out at this point. Right? That's technically a slightly different case, but the same conclusion. If at any point we can't traverse with our letters because there's no child edge starting with that letter, or it doesn't match the remainder of the label of the edge, then we fall out and the pattern doesn't occur. Technically, there's a third case that we run out of tree, we continue reading the pattern, and we reach a leaf and can't continue. Now, it turns out this is, for our application, this can never happen. As long as our pattern doesn't contain the end of word marker. So normally we have a text and we assume we are looking for some actual string in the text, not something involving this dollar symbol. And so if the pattern does not contain the dollar, it can't ever finish reading the label because all the labels leading to an edge must stop with dollar. That's the end of the text. So we can never really reach a leaf. So if dollar not in P. If you include that case, you can also handle it. It's not not necessarily a problem, but we don't normally have to worry about it. Okay, slight nitpick. How long does this take? So it takes us order P time, the length of the pattern, to find that we're in one of those three cases. But then what do we do with that if we're in case 2 where we have matches? We can find with this green pointer from before to the leftmost leaf, in constant time we find one occurrence. If the goal is to find all occurrences, then we have to output all occurrences. So we can't do that in just that time. So if the problem is to find any occurrence, we can do it in order P time. If we want to find all occurrences, we have to walk through the entire subtree and output all leaves that we reach. And that can take more time if there are more occurrences than the pattern's long. That's possible. Okay, we've discussed most of these already. some other examples. Let's come back to something similar to this opening question. That was straight string matching. In a way, we already knew how to do that. It's just now that we can build this suffix tree once and keep it, it's useful if you have to search many patterns. But let's look at a different problem where the suffix tree is of much more essential use. That's the longest repeated substring problem. We have one long string, and we're trying to find some substring that occurs at another place. So we're trying to find a substring starting at position I of length L, looking for the longest such, so the biggest L, so that there's another position J where the same substring occurs. Okay? The formal definition is just here to emphasize the two occurrences could be overlapping, which maybe is not what you immediately would have expected. That actually has use cases that we'll come back to. So it's not just an esoteric puzzle if you want. How can we do this? We definitely don't want to check all substrings of the text and check if they occur. That would be really slow. Now, again, suffix trees to the rescue. If we have something shared, some string that occurs twice, picture. So if there was an occurrence of something here and here, I'll call this P, but it really just is a substring of the text that occurs in two positions. Then there are two suffixes of the text starting here and there that start with the same string P. Two suffixes of T starting with the same text, the same characters. So this bit must have a joint path in the suffix tree because we're traversing the suffixes letter by letter. So example, in our well, this is the running example for a long time, so get used to banana ban. We have A ban and AN. So there's two occurrences of just the letter A. That's one repeated string. Now, if we look at A ban, and AN, they have this shared common path that has label A. And that's no coincidence, it's always like that. Whenever you have an occurrence of something twice in the text, there will be two suffixes that share this thing as their common prefix. And that means there must be some internal node that we reach from the root with label A, or in general, label P. So all we have to do to solve this problem to find the longest such repeated string is to go through all of our internal nodes and check if there are two leaves below them. Then the path from the root to that internal node is a repeated substring. To reformulate the question, the longest repeated substring in a text is the same as the longest common prefix, the longest prefix that's identical occurring in two suffixes. Okay? And well, you can narrow it down further, but it's two leaves. How can we exploit this? We first of all compute what's called the string depth of all the nodes. That's just the number of characters that I have to read from the root to reach that node. In a compact trie, you don't have to do that. It's actually the number that's already in that node. But let's do it here because we're storing the human-friendly version. We have to read 1A to get here. The root always has string depth 0, 1 character to get here, 3 characters to get to this one. AN is 2, another is 3, and another 2 for this one. That's all internal ones. If you worry about how to do that, again, you don't really do it. In the compact trie, you already have it. Otherwise, you could do a traversal of the tree, a recursive function that remembers the current depth and passes it down. And then the second step for finding the longest repeated substring is to just pick any node that has maximal string depth. So we could, for example, take A and A. That's one of these. And then the path to that node from the root, A and A, is one of the maximal repeated substrings. And A occurs in the suffix anaban and ananaban. So it occurs in two places, and it's actually overlapping, right? If you look at banana, there's ana and anana. Okay, do I have to write this down? So the two occurrences are ana and ana. They reuse the A, so the two are overlapping. But that's all right, that's allowed. There's a second equally long repeated string. If you pick this one instead, also has string depth 3. That's ban. And it tells you, look at position 6 and 0. Ban, ban. Right? Magic, right? No, of course not magic. It's the definition of the suffix tree. But the tricky bit again only is finding the suffix tree. Once you have the suffix tree, this algorithm is fairly simple to do. Computing the string depth is not hard, and finding the node that has largest string depth is also not hard. So we can do it in linear time after building the suffix tree. We're almost there to solve this original problem. The only thing that's missing is suffix trees so far are just for a single text. And the other problem, remember, was the longest common substring. You have several texts and you ask, what's the longest thing that occurs in all of them as a substring? For that, you somehow need to have a suffix tree for several strings. But it turns out that's actually not hard to do. There's a simple way to reuse the suffix tree as a black box and get this done. And that trick is known as the generalized suffix tree. All you do for that is define a text like this. So you take all your individual texts, T1, T2, and so on, and you add different $signs after each. So you reserve a new marker to say, that's the end of text 1, that's the end of text 2, and so on. And then you build the suffix tree for this new text, ignoring that it is composed of these individual texts. And if you look at the resulting tree, you will find that there's always some $j edges that lead to leaves, just because they occur in only one place. So you can always find for every suffix of every text, you find one leaf. So in a way, the very same trick works. It's just a neat little extra idea that's needed for that. Because we're running short on time, I don't think I'll do the question, but let's just do it together. I mean, there's 3 strings. What's the longest common substring? Because this last one is so short, we can just brute force it in a way. So BC occurs in all, I can see that here. But BCA also occurs in all 3. Good. So BCA should be it because BCAA doesn't occur. Okay? Yeah, I think that question never was that useful, but wake up time, you know, and so on. So how do we do the longest common substrings with this? Let me show the example. Maybe the algorithm we don't have time to discuss in detail. That's the generalized suffix tree for these 3 strings that we've just seen in the example. And so you see there's all the suffixes of all the strings must be there. So there must be AA from this third, for example. So you can follow A. And then there's an edge with $3 telling me, oh, this is a suffix of the third text. There are more occurrences of AA in text too. So you could also have AABCA, AABCA. That brings you to that one, and so on and so forth. So the way to construct this is put all the texts behind each other, concatenate them, and build the suffix tree for that. Now, how do we find a string that occurs in all three texts? There's one extra trick in this tree. That's these green numbers. The green numbers just mean there is some leaf below this node that has the appropriate dollar index. So the 1, 2, 3 here means I can find a 1 and a 2 and a 3 among my leaves. Whereas for this node, the 1, 2 means I only have a 1 and a 2. I don't find any $3 below me. If we have that information, we can find a deepest node in terms of the string depth, same as before. And I already put the string depth in the nodes. So this one looks like the deepest, right? It has a 3. We look for the deepest node that has all green numbers, because that means the string I can read from the root to this node, I can continue that and reach all three texts. So there's a way to extend that string to a suffix for each of the texts, which means it occurs in each of the texts. And here that's BCA, which we figured out before. All right. So that was the quick version. I spelled it out in detail as code. It's basically describing in several steps how to compute the green numbers, how to compute the string depth, and then find the deepest node in terms of string depth that has all numbers. There's not much more going on there. The only tricky bit really is to construct the suffix tree again. All right, cool. So you've seen some immediate applications for string matching and some more advanced applications where we really use the inner workings of the suffix tree to maximal extent.